let me invite Dr. T.S.S. R.K. Rao from.
Thank you, Professor Ramesha, and thanks Mahe and CRAM for this kind invitation to give a talk at this conference. Before I request the recorded lecture to be played, I would like to briefly say that even though my affiliation now shows as Ashoka University, I retired in 2019 as the head of the Indian Statistical Institute at the Bangalore Center, and I also did my PhD from Indian Statistical Institute at Kolkata during late 70s and early 80s. Professor Rao by then already left ISI Kolkata or other places, but even as a very young PhD student, I could see his influence on this entire institute. Subsequently, in my career, I met him several times and had occasions to listen to him. So it's a great pleasure for me to be able to give a talk in this conference. So now I would request the organizing person to turn my lecture on. There seems to be some connectivity issues at my end, so the lecture would play on, but I would also be here to interact and take questions. So my talk is about operators, what are called Birkhoff James orthogonal to spaces of operators. Okay, so I will mute my phone. So are there any technical issues? I'm on talk screen or audio. So thanks the organizing committee and Mahe for arranging this conference and for asking me to give a talk in this. And I am glad that in spite of all the difficulties caused by the pandemic, we have been able to continue to share mathematics by efforts of various colleagues and through online platforms. So this talk is a combination of linear analysis, functional analysis, that is geometry of Banach spaces, and approximation theory. In fact, we are going to get to some new minimax principles and apply them to solve problems in operator theory. So this title is the operators, Birkhoff James orthogonal to spaces of operators. And for real Banach spaces X and Y, I will only be talking about real Banach spaces. And L of xy denotes the space of all bounded linear operators. Then, if you take a closed subspace Z contained in Y, you can look at the space of all operators from X taking values in Z, that is L of xz. That is a subspace of the space of all operators L of xy. And on the space of all operators, one has the usual operator norm, which is the supremum of t values of the vectors over the unit ball. So one of the questions of interest that one can ask is I will just define this formally in a minute. If one could look at the Birkhoff James orthogonality in the space of all operators and relate the orthogonality to a subspace. So not orthogonal to a vector, but like in the case of the usual Hilbert space orthogonality, you can look at set of all vectors which are orthogonal to a given vector and look at that set now. And you can ask if one can actually describe such a set, and of course relate it in the spaces of operators, not just in an arbitrary vector space, but in your vector spaces of operators. So now I'm going to just read the abstract before I simply explain the terminology using my electronic board. So here is the abstract. So the important question is that if you have a T that is orthogonal to this space L of xz, then can you find a vector, unit vector x0, such that the norm of t is attained at that vector x0, and the value, the vector t of x0 is orthogonal to y. So this is somehow tries to relate orthogonality of an operator to a collection of operators to orthogonality of a vector to the corresponding subspace. So that is the challenge. You have only information globally, then can you actually get local information? The orthogonality here should imply for some vector x0 where the norm is attained, t of x0 is orthogonal to this. So in order to achieve this, so as you can see somehow, since this is supremum, and when you reinterpret orthogonality, you will see that it's actually an infimum problem. So in order to achieve that, you have to develop a compact optimization for the space of all. Well, I try to do this problem initially in the spaces of compact operators, and I would need to then develop a minimax formula which would allow me to estimate the distance between an operator to the subspace of operators, distance between t from L of xz in terms of point-wise best approximation, so that this approach links what is called a local optimization to a global optimization problem. So this independently, somehow these ideas are of interest to people working in optimization theory. One of the things when we look at the problem, you realize that most often this kind of problems involve what are called selection theorems. And selection theorems are the kind of a thing which would allow you somehow to choose what is called a selector having certain properties. But it has been well understood in linear analysis that getting a linear selection is very difficult. Somehow you can get a point-wise selection, but to make this map linear is something quite difficult. There are very few linear selection theorems, and only in case of very good spaces like Hilbert spaces and things like that. So in general, these questions are difficult to answer. So what I would do in my approach is to bring in techniques from geometry of Banach spaces to solve this problem. So here is then our background is the space of all real Banach spaces. So X is a real Banach space. If you look at a vector X belonging to X, you would say that X is orthogonal to Y. So this is a notion due to Birkhoff and James. So we used to continue to use the perpendicularity to denote the orthogonality. Here, if provided, if you look at, so X is a Banach space, there is a notion of a norm there. So if you look at norm of X plus lambda Y, that would be bigger than or equal to norm of X for all scalars lambda. So for all scalars lambda, if you know that the length of the vector norm of X plus lambda Y is bigger than or equal to norm of X, then you would say that X is orthogonal to Y. And it turns out that in case of a Hilbert space, this notion of orthogonality coincides with the usual notion of X is with the notion of inner product of X with Y being 0. That is the notion of orthogonality in the Hilbert spaces. And unlike the case of a Hilbert space, the Birkhoff-James orthogonality is not symmetric, nor is it additive. So X is orthogonal to Y need not imply Y is orthogonal to X, or if X is orthogonal to Y and X is orthogonal to Z need not imply X is orthogonal to the sum vector Y plus Z. So this is somehow more restrictive notion, but it turns out over the years this has been a well-studied notion, and it does give a lot of information even in the case of a general Banach space about the structure of the Banach space. So this is the basic notion, and the thing that we want to understand is this notion in the space of bounded operators L of X, Y. So if you have an operator T and if you have another operator S, and you want to look at the notion of when is T orthogonal to S, is it some way related to, for some points, the corresponding vectors T of X being orthogonal to S of X? So that is the basic question. Can you relate or understand the orthogonality, Birkhoff-James orthogonality in the space of L of X, Y in terms of orthogonality of the corresponding vectors in the range space for a suitable vector, appropriately chosen vector X or chosen set of vectors X? So that is the question that one wants to answer. And the reason, of course, why these things need to be studied in the general context is that even when you start with a Hilbert space H, then the minute you look at the space of all bounded linear operators, that is only a Banach space. So no longer you have any inner product structure here. This is just a Banach space, and the orthogonality then you can study here is the Birkhoff-James orthogonality. And this talk in part is motivated by a well-known theorem of my colleague Rajendra Bhatia from Ashoka University, also at ISI. So this and a well-known linear analyst and also colleague to several of us, friend to several of us, Peter Semrel. So this Bhatia-Semrel theorem would say that when H is a finite dimensional Hilbert space, I will write it in the next page. So for a finite dimensional Hilbert space, this would say that if you know that T is orthogonal to S, then there is a vector x0 of length 1 such that T attains its norm at this vector x0. So remember, let me recall what is the norm of the T for you. This is holds for any space, Hilbert space or general space. This is supreme over all vectors of length less than or equal to 1 norm of T of X. So in finite dimensions, of course, because of the compactness, Hein-Borel theorem, compactness of the unit ball, a transformation would attain its norm. So this is saying that there is when it is attains its norm, it will be at a unit vector. So there is a unit vector where the norm is attained and such that T of x naught is then Birkhoff-James orthogonal to, or orthogonal in the Hilbert space sense to S of x naught. So this is a very beautiful theorem which would say that orthogonality with the operators would actually mean that there is a point where the norm of the operator is attained and the corresponding vectors are orthogonal to each other. So this has generated in the past 2 decades a lot of interest, and one of the things it turns out is that this is no longer true in infinite dimensional spaces, and also even in finite dimensions no longer true if you don't take a Hilbert space. So this is something which is special to Hilbert spaces. So what one would then like to understand, the research that has been generated by this is somehow to understand the notion of Birkhoff-James orthogonality when you have general Banach spaces x and y, and try and see if you can relate this kind of a point-wise relation you can get out of the general orthogonality. So one of the things then you can talk about is that you take any subspace Z contained in a space Y, a closed subspace for me always, and you are looking at the space of all operators from a Banach space X into Z as a subspace of space of all operators from X into Y, and then you take an operator T which is such that T is orthogonal to all the operators in L of xz. So this I will write it as T of orthogonal to L of xz, means that for each S, T is orthogonal to L of xz. So instead of looking at a single operator, as in the case of Bhatia-Semrel theorem, I want to look at this subspace of operators, and I want to look at T orthogonal to space of all operators, and ask a similar question, namely, when can you get a unit vector T such x naught such that norm of T of x naught is equal to norm of T, and this vector T of x naught is now orthogonal to this subspace Z. In other words, it is orthogonal to all the vectors in Z. So instead of looking for one vector situation like the way I illustrated Bhatia-Semrel theorem, the more general problem in the context of Banach spaces can be formulated like this. For a closed subspace Z, if you have an operator T such that T is orthogonal to all of L of xz, then is there a point x naught such that norm of T of x naught is equal to norm of T, and T of x naught is orthogonal to Z. So then one of the things which is also true in case of Bhatia-Semrel theorem also here is that the converse is always true. In other words, if you can find a unit vector x naught such that norm T of x naught is equal to norm of T and T of x naught is orthogonal to Z, then T is orthogonal to L of xz. So this is easy to see. Take any S in L of xz and then look at norm of T plus lambda S to show the orthogonality. That is bigger than or equal to its value at the unit vector x naught. So I write it as now T of x naught plus lambda times S of x naught. Okay, but I know that T of x naught is orthogonal to Z, and S of x naught, since S is an operator from X to Z, S of x naught belongs to Z. So by hypothesis of pointwise orthogonality at the vector level, this is bigger than or equal to norm of T of x naught, and of course norm of T of x naught we said is norm of T. So we have proved that for any S belonging to L of xz, norm of T plus lambda S is bigger than or equal to norm of T for all scale S lambda. So that means T is orthogonal to the operator S. So that this is clearly a necessary condition, and what we want to look at is to see that when under what conditions is this a sufficient condition. So this is the minimax formula that I want to develop, and somehow these kind of things have been looked at by well-known approximation theory people. This is William Light and E.W. Cheney. This is a monograph by them called Approximation in Tensor Product Spaces, and one somehow knows that there is a close relationship between tensor product spaces, particularly injective tensor product spaces, and compact operators. So this is somehow the kind of setup one would like to know. So for example, if you look at the space of all continuous functions on a compact set K, which are valued in a Banach space Y, and look at the space of all vector valued continuous functions, you can again put the supremum norm of this. So norm of F is supremum of K belonging to K, norm of F of K, where F is a continuous function. Then for any closed subspace Z of Y, you can now look at continuous functions which takes values in Z as the space of subspace of continuous functions which take values in Y. And so this is a classical formula due to Light and Cheney would say that if you look at the distance, so the distance means this is infimum of norm of F minus G, where G belongs to CKZ. So this infimum is same as supremum of, look at the distances for each K, for each point K of K, F of K is a vector in Y. So look at its distance of this vector F of K to Z, look at those distances and take the supremum. So this is somehow a very famous minimax situation. Here you are looking at an infimum. So this is infimum of norm of F minus G, but norm itself is a supremum formula. So this is inf sup is same as sup, and distance is again infimum, supremum. So this is a very beautiful minimax formula. And so I have realized that one of the things you would like to do is to really ask if such a minimax formula is can be formulated and proved in some special cases in the case of spaces of operators and generally compact operators. So this is what we would do. So it is quite easy to see that, so let us get back to our setup of operators. So Z is a subspace of Y. We are looking at L of XG as a subspace of L of XY. So you take a operator S in L of XG, then it's easy to check that if you look at any unit vector, the length of T of X minus S of X is always bigger than or equal to the distance between T of X to the subspace Z. So now you take a supremum on both sides over the unit one and take infimum on overall S belonging to L of XZ, you realize that distance between T and the subspace of operators L of XZ is really bigger than or equal to supremum over the unit one distance between the vector T of X to the subspace Z. So the analog of Light and Cheney then can be formulated in a context of operators on Banach spaces as to ask, when is this formula valid? When can you have equality in this inequality? When can you say the distance between T and the space of all operators is really looking at point-wise this thing? So this is what I call as a local optimization, and this is what I call as a global optimization. You are looking at a global infimum, and here these are local infimums, and then you are taking the supremum over the local. So this is what I would call as the minimax formula, and one would like to know when is such a minimax formula valid. So the kind of domains that I want to solve this problem is that I look at, because the Light and Cheney's problem is situated for continuous functions, I would like to look at a kind of a class which is more general than continuous functions. These are Banach spaces which have the property that when you take the dual, then the dual is isometric to the space of all measures, space of all integrable functions with respect to some positive measure mu. So this is somehow a very natural class. When you look at LP space theory, you realize that it is possible that you have Banach spaces X such that their dual is isometric to L1 of mu. And these are such spaces that are essentially studied by a well-known functional analyst, and of course a great functional analyst, Zoran Lindenstrass. And Lindenstrass has studied it, and his monograph is called Extensions of Compact Operators. So it is clear that somehow these are the kind of setup where you would like to solve the kind of optimization problems that I am looking at. So I look at these class of Banach spaces to solve this problem. So then there is associated with this subspace L of xz, you can look at the quotient space L of xy divided quotiented by L of xz, and then you map it into operators from x taking values in the quotient space y over z. So z is a subspace of y, so I have the quotient space y over z, whereas L of xz is a subspace of L of xy closed to subspace, so I have this quotient space of operators and send it to the space of operators, and this is the map. So pi denotes the quotient map on all spaces. So you look at phi of pi of t. This is any element here is looks like a pi of t, where pi is the map from L of xy to this quotient space. So phi of pi of t is look at the corresponding quotient map here and take the composition. Now one can easily check that the minimax formula I am asking is to say that when is this map phi is an isometry. So what we started out as a minimax formula is turns out to say that when is this map is an isometry, and philosophically this is also a very important problem in Banach space theory. Namely, most often you have these are spaces you have pointed out by another space of operators, and then you want to say when can this be realized as space of operators in some other sense from x into, of course, different range y over z. So this is again a very classic problem in Banach space theory, and one is actually attempting to solve that problem also here. And somehow this turns out that you would need a little more extra geometric information in order to do this, and then if you do that, then the main result will be the following. For a separable and reflexive Banach space, my domain is like Hilbert space, for example, is a reflexive space, and most often it is enough to consider separable Hilbert spaces. So similar to that, I take my domain as a separable reflexive Banach space, and y is a z is a subspace closed subspace of y, and now I put some geometric conditions on z. Z is an L1 pre-dual space like the one way I have defined before, and it also sits in y in a very nice way, that is called it sits like a M ideal in y. Then for any compact operator t from x to y, this distance t of t to space of all bounded operators x to z is actually attained. There is a point x naught of length 1 such that the distance of t of x naught to z is really equal to this supremum taken over all unit vectors of the corresponding point-wise distances. So this is the minimax formula. So this minimax formula validity very clearly is equivalent to that if t is orthogonal, if this compact operator is orthogonal to L of xz, then this at this point x naught, t of x naught is actually orthogonal to the corresponding subspace Z. So this is then one special instance in the theory of Banach space theory where one can do an analog of Bhatia-Semrel theorem on Hilbert spaces and much more, because somehow Bhatia-Semrel theorem is about only two operators being orthogonal to each other, whereas I am solving this problem for an operator t which is orthogonal to the space of operators from L of xz. Then my conclusion is that there is a vector x naught where the norm is attained such that the corresponding vector t of x naught is orthogonal to this closed subspace Z contained in Y. Of course, G has to be a special subspace of Y. Then this problem is solvable. So I hope I have sort of communicated to you a lot of interesting thing in geometry of Banach spaces. Things somehow which work quite neatly in case of finite dimensional or infinite dimensional Hilbert spaces are enormously more difficult to solve when you formulate and try to solve the same problem in the context of general Banach spaces. So I would like to stop here and take questions in a subsequent few minutes. But let me finally show you my references. So these are my references. So this is the paper of Bhatia and Sembrel that I'm talking about. This is from linear algebra and applications in 1999. And this is the monograph of Light and Shinnick, which is about approximation theory in tensor product spaces, where they have somehow attempted to solve some minimax problems in long time ago in tensor products. So when I wanted to do the same in spaces of all operators, so that would be my starting point. But then since these things involve selection theorems, I had to apply tricks from geometry of Banach spaces to overcome the difficulty of choosing a linear selection. And there has been a lot of interest in Indian colleagues also and others in this area of Birkhoff James orthogonality. There is a nice survey article written by two colleagues from Jadavpur University, Kallol Paul and Devmalya Sen, Birkhoff James orthogonality and its applications in study of geometry of Banach spaces. It appeared in 2019 in this proceedings. So that is a very good point to start the study. And I think the general theory of tensor products is the monograph by Ryan is introduction to tensor products of Banach spaces is a good place to learn tensor product theory. So thanks once again for arranging this meeting and giving me this opportunity. Thank you.
Thank you, sir. Any questions? Manjuna, shall we wind up? Yeah.
So, thank you very much for patiently listening to me, and I'm glad well without taking.
Yes. Join us. So thank you, sir, Dr. Professor TSS R.K. Rao, and also Augustine Marguerite for their excellent lectures